The first speaker is Alex Ochirov, classical scattering of spinning black hole from quantum amplitudes. Please.
Thanks for inviting me to speak. So I want to talk about some aspects of spin regarding the transition between quantum amplitudes and the classical scattering, and the results that I will be presenting will be the basis of this talk. Were obtained in these two papers with Alfredo Guevara and Justin Vines. Well, in this workshop, we have seen a lot of newer results for classical binaries using amplitudes methods. And in this talk, I want to really talk about some spin aspects. So I want to aim, I want to elucidate some spin aspects of how we take the classical limit. And the focus of this talk will be really the simplest one, the 1 p.m. tree-level scattering. And in this setting, I want to explain to you how this classical scattering observables, delta p, so the momentum impulse and the linear impulse and the angular impulse in classical scattering can be extracted just from the physical information in this tiny amplitude first written in this paper. So, and these aspects of the classical limit, they are covered to some extent in these 4 papers, even though the last one doesn't even talk about gravity or spin, I think. So I want to really breach some gap in the literature, which is not really a gap if you read all 4 of them and then think, but maybe it's this will be somehow illuminating for some, or at least amusing for others. So the outline of the talk is really that I want to start from these building blocks that I just mentioned here. I want to really explain how I write them with, what I write them with, and then I'll go to how we start extracting some spin operator information from these amplitudes, and then some aspects of the classical limit that involve spin coherent states. And well, in this talk, I have more slides that I really care to cover in detail. So the results that I have presented multiple times in more detail are, of course, also in the talk, but I won't be, it's fine if I don't get to cover all the details there. So please ask questions at any point, because I've given this talk multiple times already, and I'd prefer it to be more amusing than just running through the slides. So yeah, I want to start really low from 3-point gravitational vertices, and just to remind you where that kind of amplitude can come from. So the 3-point amplitude can just come from the post-Minkowskian expansion of the metric tensor, and expanding the minimally coupled matter Lagrangians in this H, one can read off vertices. So this is the scalar vertex, and this is the spin 1 vertex. So you can see that increasing spin by 1 produces quite a lot of new information at the level of the off-shell gravitational vertex. However, if you put them on shell, then and use the spin and helicity notation, you can start seeing that they are not that different. So the spin zero amplitude, which is obtained with from the vertex by contracting basically, by contracting it just with one polarization vector or tensor, in this case, is this, where X will be used for this gauge invariant helicity factor, which is introduced dimensionless. And for spin one, the difference is that you start having these spinor products where there's a certain kind of total antisymmetrization in the Lillie group indices that I want to talk more about. And well, this is obtained from this vertex by contracting it with the polarization tensor for the graviton and also with polarization vectors for the massive spin one particles. And then that's the simpler result that you get. So, well, we already see and can imagine that this is just a simple example how spin helicity helps with the level of complexity that you see at the off-shell level that gets reduced drastically when you go to the on-shell level. And the reason for that is, of course, that Feynman rules usually give you some function of momenta, polarization tensors, which are gauge dependent, and spinors if you have them. But all of their Lorentz indices have to be contracted, and the real degrees of freedom are really helicities for massless particles, and SU2 spin labels for the massive ones. And this is the basis for the reduction. And the Lillie group, the spinor helicity allows you to really be covariant with respect to the Lillie groups of the particles, which are much simpler than the Lorentz group that is evident from the off-shell vertices. Because, of course, the vertices care about fields. You can construct field correlation functions using them, but amplitudes are really simpler objects. So, so this is some motivation why it's nice to use spin helicity. And this slide has a lot of different identities in spin helicity that all start with the spinor map, where you replace vector index mu by two spinor indices, left-handed and right-handed, which is dotted. And most of you hopefully have somehow seen the massless spinor helicity formalism before, and are used to seeing the spinor products written with angle and square brackets. Well, in the massive case, now you have an explicit index A or B, which is an SU2 index, and many properties are somehow blown up to something slightly more involved in the massive case. But the spinor products are, of course, still antisymmetric, because SL2C respects the Levi-Civita contraction.
Alex, sorry, super dumb question. So your indices A and B, for spin J, they run from -2J - 1 to 2J + 1 or something like this?
Sorry, A runs from 1 to 2, so it's an SU2 index. And when you have spin S, you usually have you have
more A's
with an antisymmetric, with a fully symmetrized tensor with 2S indices. And the first time something like that appeared was here, where spin 1 was obtained. A spin 1 polarization vector was obtained with with spinors. Each of them has an SU2 index, and fully symmetrized.
Okay, thank you.
Excellent. So, yeah, and well, if you want to use that formalism in the usual QFT language, in the Q frame setting, you just need to introduce external wave functions using holistic spinners. And in the massless case, it was done quite a long time ago. And of course, in the massive case, we now know how to introduce polarization tensors as well. So the polarization vector, as I have already introduced for spin 1, and for spin s, you can have symmetrized tensor products of these vectors, and those will be correct polarization tensors. So here again, those two simple amplitudes that that I started with. Now you understand what is happening here. And now I will introduce this notation where I will make the jump to spin s, and instead of writing something like 1, 2, A1, B2, B1, and 1, A2S, 2, B2S, and fully symmetrizing all the A's among themselves and fully symmetrizing all the B's among themselves, I will just write this symmetrized tensor product symbol here.
We cannot see what you write. Yeah. We cannot see what you wrote.
Oh, what? Why?
I don't know.
Oh, it froze. I see it. It just
doesn't appear.
My Zoom froze, I think.
Mm.
Yeah, it's reconnecting.
Okay.
Why is it doing it now? Okay, I think it's back on again. Okay, I'm allowed to screen share again. And there I go. So,
now we see.
Yeah, so as I was saying, instead of writing this whole symmetrized tensor product, I'll just write this. And now these amplitudes are minimally coupled spin s amplitudes for a graviton. So 3 is a plus or minus holistic graviton. So, well, let's now try to connect these amplitudes to something that was in the title, black holes. And for us, the first hint for that was when we rewrote these amplitudes in this form. So instead of left-handed massive spinners, we rewrote them using realistic plus. We wrote them using right-handed, and we saw a certain exponential in spin operator. And it turns out that in the classical case, Justin has taught us that the stress energy tensor that you could use as an effective source for the linearized curved black hole could also be written using a certain exponential in spin. So I will, throughout the talk, I will be using either spin or a spin length A, not to be confused with the logarithmic index, which are just related by a factor of mass. And this exponential can be written on shell if you convert this word line source to an actual vertex. You will see that what you get is some exponential of the classical spin that we also see a similar exponential in this minimally coupled amplitudes. So the difference here is, of course, that this exponential is a full exponential to infinity with the sum to infinity, whereas at any finite spin s, this exponential is a polynomial, which is cut off at some point. But in the limit where s small s goes to infinity, these exponentials really have the same kind of information. So
Sorry.
these exponentials, yeah.
I didn't follow that truncation.
You didn't follow
the truncation arguments.
Oh, the truncation. Well, yeah, the truncation, you have to, it's slightly non-trivial because indeed, if you want to open this exponential, you start with an infinite sum. But if you, but at some point they will, you will run into objects like 2k, k, and then it will somehow be contracted with k, 1, and say b1 and 1. And when you contract them, you just get 0. You will some massless spinors of your exchange momentum k, which are massless, will be contracted between themselves, and you will get a truncation after some order. So yeah, it's the way when you write the exponential, you don't. It's non-evident. And well, and the point is, of course, that this exponential is the contains the spin-induced multiple structure of pure black holes, and it seems like these minimally coupled amplitudes have the same spin multiple structure. And well, this exponential, the slide is about rewriting this kind of exponential with polarization vectors sitting in a slightly weird way to a different kind of exponential where I have introduced, instead of a spin tensor, I've introduced a spin vector operator. It acts on the spinor indices using also via the spinor generators of the Lorentz group, but it's a Pauli-Lubansky vector analog of the sigmas. And the 3-point kinematics allows us to really rewrite this exponential as this exponential. And I will be using this exponential because it's just simpler. But we saw it slightly later that this exponential can also be written. And so at the moment, what I'm doing is really I'm trying to take those amplitudes that they're kind of opaque with respect to what kind of spin operator dependence they have inside of them, and rewriting them, exposing that spin dependence. And this spin dependence, well, this slide is to also tell you that in the spin operator, even if you introduce it in vector space, or in the if you introduce some polarization tensors for spin s particles, then you will be introducing a Pauli-Lubansky operator using the generators of the Lorentz group for some tensor representation. And if you compute this kind of spin s one particle expectation value, you will get a very nice spin quantization here in terms of some unit spin vector. So really, this really covers all the 2s plus 1 polarizations along this vector. So okay, And I guess the important thing for later is just to remember that you can start with a polarization with a spin vector which acts on spinor indices, which are SL2C indices, kind of off shell. So here I'm acting off shell, and obtain a spin, still a spin vector, which still has a lot of indices, but now these indices are physical indices A and B. Those are physical indices of a massive spin S particle. Well, yeah, let me skip the slide. I want to, which was important, but this is some kind of trick where we also expose some residual spin dependence.
May I ask just
Yeah,
one little point of clarification? So
yeah.
these vertices are given a completely fixed.
Yeah.
Completely, because there is no free parameter, since we know how the graviton couples at zero momentum. So
yes,
everything else is fixed.
Yeah, and well, the black hole is a fixed object as well. So it's
yeah, supposedly.
And yeah, and it obviously
because of the no hair. Yeah.
In this talk, I focus on the black hole case, and the more general case has been also considered by the group involving Zvi Bern, Ryder Royban, Xiao Shen, and Mao Zheng, and Andres Luna, Mikhail Solon. I hope I'm not forgetting everybody who was involved in that, and they are being careful in considering the general case where all the spin multiple couplings are not fixed to some combinatorial factorials, but in the black hole case, they arranged very nicely in some exponentials, and that's what I am talking about here.
Yes, thank you.
Yeah, and so in this slide, I'm basically proposing some kind of heuristic jump from the amplitude, the minimally coupled amplitude that now I wrote, extracting just the spin zero part, the scalar coupled to a graviton, and then I rewrote it either in this way or in this way, and in either case I see this exponential, and in the classical limit that is here, I want to really just read off this exponential and times the spin zero part. So I want to now, so this is like a sketch of how we were doing this. And well, there's more details that I have glossed over, but in both of the papers that I advertised with Justin and Alfredo, there was still some level of heuristics involved. And I'm hoping to also cover that to fill the gap in making those heuristics slightly or maybe actually fully rigorous. So this leap here, it again, at this level it's this operator that I understand as some matrix, multi-indexed matrix operator acting on all the spinor indices of this horrible fully symmetrized spinor product, no, tensor product of spinors. And but here I want to understand it in terms of just the classical spin length A, and remove that junk away, which is some unitary stuff. So and well, so far I've been trying to breach this gap in trying to start with quantum amplitudes that involve just a integer valued spin number to well, a quantum number, to extracting the classical spin dependence, where the spin is really some 4-vector transverse 4-vector. And well, again, what I'm going to tell you is based on these 4 papers and maybe more. And well, the rigorous, for me, the most rigorous way to understand this classical spin, the classical limit from Q of t to classical field theory, is the Kamak formalism with the spin version of it. And if we are at 1 p.m., we can forget about some terms that I omitted and just have the linear term in the amplitude, which you need to Fourier transform using your impact parameter. And do some something here, and what you get is the classical spin momentum impulse, and also the spin kick can be extracted in a more involved fashion, but also you have to perform the Fourier transform and understand these the amplitudes as some operators in the physical space of Lillie group indices. And so this S mu here is acts on this Lillie group indices as well, and you can construct this commutator. So you can think of this as mu. So A here, well, this A is just the particle number, the black hole label. But the point is that this S here in this formula can be understood as that thing that I wrote before, where you have polarization tensors, and for particle 1, it has all the indices it needs to have, 2s, and then this guy also has all the indices it needs to have, and all the tensor indices are contracted here, and so this spin operator is understood as well, let me also conjugate that. So conjugation in SU2 brings down indices down, brings the indices down. So what you get is this kind of operator. And that's how this commutator is constructed. Now, these formulae contain more terms, not more terms, well, more ingredients that involve contractions with certain wave functions that are not nicely peaked in the classical sense. So when you take the classical limit, you can read off your classical charges like momenta. So for momenta, that basically means that when you evaluate these brackets, you let your exchange momentum k go to 0 because you factor out an h bar from it, and also the momenta go to classical for velocities. And similarly, something like that must happen for spins. So you started with some quantum spins, and you want to read them off as classical spins. And
we have not seen what you wrote.
Oh, it froze again.
No, now it's written, but was not on the screen.
Oh, I'm sorry. Yeah. Well, actually, I think I'm seeing exactly what I'm seeing here. So maybe your screen is slightly cut off. But anyway, I was just underlining something.
Okay.
But I think it's quite well synchronized now. So for momenta, that was well covered in the original KMOC paper, where the momentum wave packet is in the relativistic case, which is what we're interested in, is proposed to be this. It doesn't have to be that exactly. It just needs to have the similar properties to what this is, and and it looks like, even though in the rest frame it starts looking like the Gaussian wave packet around some momentum, and so and there's the difference between what happens with amplitudes for spin and momentum, obviously, because amplitudes are already functions of continuously changing momenta, but it might be confusing. It was certainly confusing for me to deal with how the amplitudes have a little group index dependence on spin rather than some continuously changing spin inside of them. So we need to construct something similar. So we need spinning wave functions that behave in a similar way, that their expectation values when calculated using those wave functions goes to the classical value, and also whatever polynomial you have. For example, when you have two spin vectors, you should also get in the classical limit, you should also have just a polynomial dependence on the classical value. So this extra bit should be negligible in the classical limit. So we need something like that. And that's what I wanted to cover in this talk in more detail. And to do that, I want to go down to a new low in the triviality of things that I might be covering, at least from the point of view of some of you. I want to go back down to the harmonic oscillator, the null problem of quantum physics. So if we shortly forget all that I've been saying, let's just consider a harmonic oscillator. And if you just consider its energy spectrum, well, and want to take its the classical limit of the states in this basis, then you have a problem that if you want your energy in the classical limit to be finite, you need to not only put your h bar to 0, but let your occupation number go to infinity. But when you do that, at the same time, your error in momentum and position will also be classically finite. This is not what you want in a classical limit. You want the sharply peaked value for your observables. And well, probably, and I'm sure most of you know the solution to that. You must introduce coherent states, starting with the creation and the annihilation operator, you can just introduce the coherent state alpha in the following way. Where this is the vacuum of your oscillator. And from this, you can immediately obtain the other defining feature of this of the coherent states, is that they are they diagonalize the annihilation operator, and you can also, of course, by definition, expand them in the energy spectrum in the Fock space basis, and you get an infinite number of non-zero coefficients. But here's what you get for the expectation values. So for any operator that is some function of creation and annihilation operators, where order is important, you can construct a you can reduce it to the normal ordering, normally ordered form, and get the expectation value like this. So what does it mean for different observables now? It means different simple things, I guess. So delta P is something like that. Like that. And importantly, the occupation number for the states is alpha squared, whereas the energy expectation value is related to the occupation number. Whereas the deltas will become nicely independent of alpha, and so they will realize the best classically possible states. So in the classical limit, we tend H bar to 0, when at the same time we need to, if you want the energy to be finite, we need to consider that alpha goes to infinity at the same time as h to the minus half power. And so what you get is, in this classical limit, for any operator, you will, getting it to the normal ordering form will be free, because one behaves as one is finite, and A and A they behave as alpha, so they go to infinity. So in the classical limit, these operators start to commute, at least when you sandwich them between the coherent states. And also any two operators, when sandwiched between these states, will behave nicely as classical objects times O2 alpha. So okay, so this was really some review of what probably everybody should remember, but maybe not everybody does. And now the same stuff is what underlies the classical limit for spin. So what I want to show you now is what is the spin coherence states formulated by Schwinger a long time ago. The only difference will be that I will be writing that stuff in the spin-helicity language. So that will be, I guess, maybe the new thing. So the starting point for spin will be introducing two creation and annihilation operators. So I will index them with A and B, which are 1 and 2, which are SU2 spinor indices, the same ones that I was using in the massive spinor helicity.
You have spoken for 40 minutes.
Yeah, thanks. So so sorry about the fact that I have the notation A for the operator and A for the index, but they're always in the same upper or lower case. So it's I hope there's no problem here. So conjugating SU2 indices means putting them down, and Schwinger's construction for the spin operator. So this is the spin operator that you can understand as the rest frame spin operator, can be written as follows. You take your fundamental representation of SU2. You use, of course, the Pauli matrices for that, and you contract their SU2 indices with the indices of your equation and annihilation operator. And from that, you can immediately derive that these operators will be general quantum mechanical operators for angular momentum. So in this way, you can construct an arbitrary spin representation of SU2, and you can introduce an SU2 covariant J spin. So now I'm using J instead of S, just because I want to follow more quantum mechanical notation. An SU2 covariant J spin state. I will again use a number of a 2J number of those indices, and they will be fully symmetrized just by definition, because the way I introduce this the state is by acting 2J times on the vacuum. So the vacuum now is just the scalar state. It's the spin vacuum. So these are fully symmetrized, and if you want, you can always connect this to the standard definite spin and spin projection basis with some combinatorial factors. What you get is you take some of the indices to be 1s and some of them to be 2s, and the number of how many you take determines your spin spin projection quantum number. So once that's introduced, you well, you know what? So this is like the Fock space. Fock space for spin. Now I can introduce, but now I have creation and annihilation operators with respect to which I can introduce spin coherent states. So now my alpha belongs to C2. It's a spinner. It's like a standard quantum mechanical spinner. And I'm allowed to take this contraction of creation operators and act on the scalar state. And by analogy, all of the arguments go just the same way. What I get is that it diagonalizes the spin annihilation operator. And this alpha also can be expanded in the Fock space, and that involves a summing over all integer and half integer total spin quantum numbers, and then you can either sum over all the indices, SU2 indices, and do it like that. So this is what I used to call alpha to the tensor power 2j. And if you contract this in this way, you get a spin coherent state from the definite spin states. The same can be, of course, written for in the other, maybe more familiar basis which is not SU2 covariant. You fix some of the coefficient, some of the indices to be ones and some of the indices to be twos. And there you have your expansion in terms of JM spin basis. Great. So why have I gone through the trouble of these definitions? Well, the thing is that just as for the harmonic oscillator, I can now compute what the first of all what the spin expectation numbers are, and the expectation number is just this spin contraction, spinner contraction with these alpha spinners. And in the classical limit, again, we not only take h bar to 0, but we take the square root of a. So I was calling this alpha squared, but it's really a contraction now. So I understand this as going to infinity as h to the minus half power of h bar. So in this case, j expectation value is finite, but also any polynomials in J will behave as they should. And well, there will be H, the rest will look like this. Plus alpha. So this is negligible because it's of h bar, even taking account of this alphas. So that's it. That's it for the rest frame spin construction. So these J's should be understood as boosts of what I was talking before. In the previous sections, I was talking about covariant spin vectors and tensors with Lorentz indices. Now, well, it's a Pauli-Lubansky spin operator. And now I just boost it to the rest frame, and in this rest frame, all this construction makes sense, just as in quantum mechanics. So I think that's that's what I wanted to cover to hopefully to make some things clear about what kind of machinery goes behind, what kind of machinery is behind these wave function business that's put inside these this classical limit brackets. And well, that's I'm thinking close to my time, so I still wanted to get to Justin's classical solution, and to do that you need to consider this cut amplitude. In the classical limit, you can consider the exchange momentum being small, or actually put it on shell first using the holomorphic classical limit. So in this limit, you really factorize it onto two on-shell amplitudes that I've been talking so much about. And when I wrote them using these exponentials, now these exponentials, if you realize that this amplitude should be put inside those brackets, all of these indices, all of these SU2 indices that are still free here, they're not explicitly written because there's too many of them, so they are in this in this heuristic tensor products. They are still free, so this amplitude is a huge operator. But if you contract it properly with all those indices of the spin coherent state representation for in which is peaked around some classically relevant spins, then you can really read off this operator as a classical vector, A and A B for two black holes that scatter. And so this is the kind of Fourier transform after you take the classical limit and do the wave function business. Now it's just a function, no indices anymore. And then it contains all the same information, but after gluing two ingredients here. And from it, you should Fourier transform it further to impact parameter space, and then you have this log dependence. And finally, when you sandwich it in this formula with where you actually have some non-trivial you don't in the KMOC formulas, you don't just Fourier transform the amplitude, you Fourier transform the amplitude with the momentum or with the spin operator, but you can understand all of that as some kind of partial derivatives acting on your Fourier transform. And so once you do that, you really can read off Justin's 1 p.m. impulse formula on the nose. Yeah, sorry for running over time. I think I can just skip to write to the outlook and the summary, saying that and just say that I think we now understand pretty well how the classical limit works in presence of spin. It's and it involves at least some of the ingredients that I covered in this talk. So thanks for your attention.
Thank you, Alex. We have 6-7 minutes for questions. Other questions? Either you raised the hand or you just talked.
Let me ask a question myself.
Yeah.
Very nice talk, thank you. I wonder whether with this formalism you explained at the end with these coherent states for spin, do you really need the machinery of this helicity amplitudes? I mean, can't you shortcut the procedure and jump directly to the...
Well, that's what we were doing in the first place.
Yeah.
So the papers that I was kind of presenting that were written in, what was it, 19? I'm forgetting. Yeah, 18. At the end of the 18 and 19, actually have shortcuts. The first one loop paper even more so than the second. So heuristically, Alfredo is a master of doing heuristic jumps that turn out to be correct. And what I was trying to convey in this talk is that those heuristic jumps all along were well justified. Yes. And indeed, you can do them, yeah, if you do it like that, you don't need all this machinery. You can, but if something doesn't work, at least when you realize that this is what should probably be behind the scene, working behind the scenes, then you can maybe see what's what and find your mistakes if something doesn't work. So okay. in the papers we were presenting what works. So it turned out that everything was well footed in the stuff that I, for one, realized much later than we did that.
Mm-hmm. If I might interject and add to Alex's reply, one can also do morally the same with sort of related coherent states and not refer to helicity amplitudes, but rather construct spin vectors or spin tensors as expectation values of Lorentz generators.
Yeah.
Yeah, absolutely. Yeah, and I was doing the same thing, right? I started with the spinor helicity amplitudes, but then I rewrote them using generators. They were in spinor. There were spinor generators because I was dealing with spinors. But yeah, you can do the same in the vector language, and those will be vector generators or tensor Lorentz generators.
That's right. Yeah, Lorentz generators in spin S representation, if you wish.
Yeah, absolutely. Yeah, I even had a slide where I was using specifically spin S tensor generators. So yeah, in any case, you can do that, and if there exists a set of well-behaved coherent, even not necessarily the coherent states that I was showing, it just has to be something similar with similar properties. Just coherent states are an example that is very pretty. Mm-hmm. It exists.
Maybe it's also worth adding, the coherent states are great for many things, but when you're taking expectation values, you need to be a little bit careful that if you're taking expectation values of some say some amplitude that you've expanded out. Maybe you've written it out in terms of spin generators. Radu says you've generated one spin S representation. But you can encounter commutators of these spin generators. It's important, you know, to be careful taking those commutators. The commutators, you know, may or may not be relevant classically. It all depends on how things assemble themselves.
Absolutely. So to avoid this, all you have to do is, if you have a product of generators, all you have to do is decompose them into symmetric combinations. And after that, the limit is sort of smooth. There are, of course, for each of these symmetric guys, there are subleading terms similar to the ones that Alex wrote at some point. But occasionally those guys happen to be important too.
Yeah, they do. Yeah, that's right. Exactly. Yeah.
Thibault has a question.
Yes, concerning the 2 p.m. result. Okay, with Donato, we had computed classically the linear in spin. I mean,
absolutely.
The spin kick. So, what is you said it matches. So, is your result confirmed by another calculation? The full?
Oh no, not the full one.
At 2 p.m. level, what is what is conjecture and what is known to be true?
So
can I take this, Alex?
Oh yeah, if you want.
So yes, certainly it matches your result with Donato at linear and spin. Recently, there were works from amplitudes groups like Andres Luna and Dimitris Kosmopoulos, where they looked at doing the honest 2 p.m. or one loop calculation with spin squared. And also the day before that from Rafael Porto using their Wordline EFT with spin. They confirmed the aligned spin scattering angle that was conjectured through spin squared. Yes, you have this here. Beyond that, there's spin cubed and spin to the fourth, which were also conjectured. They're certainly not fully confirmed, but there's a demonstration of agreement with self-force results in the paper by Neil Siemens and myself from 2019. So so there is still some unconfirmed conjecture in the 2 p.m. aligned spin angle up to spin to the fourth.
Okay, thank you.
Yeah.
Okay, maybe we can stop here and have a more discussion after the next talk.